Okay, so lesson number 2 is solving absolute value equations. So an absolute value equation would be an equation that contains an absolute value expression. We can recognize them by the fact that you have your straight values, or straight bars. So the absolute value of 2x plus 3 equals 8. The absolute value of 3 plus x equals 2x plus 1. So we're going to look at solving these both algebraically and graphically. So we'll start graphically. If you are solving these graphically, there are 2 methods that you can use. You can use the intersection method, or you can use the x-intercept method. If you are using the intersection method, you have to have 2 graphs. You have to have a y1 and a y2. So if I was to graph this, clear out whatever or if any equations that you have in your y1 and your y2. To get the absolute value notation, we press math and we go over to number and it's ABS. And we press enter. And depending on the type of calculator you have, it might say ABS open bracket or it might convert it into the straight bars. So then we would type in 2x plus 3, close the bracket if yours is the ABS open bracket form. And then I'd let y2 be equal to 8. I don't need to worry about my window settings because what I'm going to do is I'm going to press zoom and standard to give me my 10 by 10 window settings. So there's my absolute value of 2x plus 3. And then my line y equals 8, and then I'm going to find the x-intercepts. So I'll start off by sketching what this graph looks like, and then while I'm doing that, you guys can find the intercepts. Okay, so what did you get for your x-intercepts? Negative 5.5 and then 2.5. So we're only interested in the x values. We don't need the y values. It's the x values that are my solution. If I told you had to put these as fractions, how would you do that? Yeah, I'd put the x and then the frac, or I could put negative 5.5 in frac. So I'd get a negative 11 halves and 5 halves. Okay, so that's the x-intercept method. That's the intersection method. The x-intercept method means finding the x-intercepts, which is finding the zeros. So in order to do that, I can only have one equation. So instead of having the 2 equations, y1 and y2, I have y1 equals the absolute value of 2x plus 3, and then I put minus 8. So I take this equation and I put everything onto one side. So I move the 8 over, which makes it negative. And then if I graph this, what I get is my graph is slightly changed. And so it is possible to have an absolute value expression but still have it in the negatives because of this negative 8, because it's moving the graph down. So if I sketch this out, what I get is the graph that looks something like this. And then I'm going to try to find the zeros. So second calc, and then the zero. I need to be on the left side of the zero, and then on the right side. So when I'm going from the left side to the right side, I'm looking to find out when the y values change signs. Press enter one more time, and there's my 2.5. If I don't get that sign change, so if I find the other zero, if I did this backwards, first of all, so that the arrows are not actually pointing towards each other, and then pressed enter again, it would tell me there's an error in the bound. So I have to quit. I have to try again. So if I don't watch for a sign change here, and I don't go far enough over, the arrows are still pointing at each other, but then when I go to calculation, I get error, no sign change. So that's what the errors tell you. So third time's a charm, left bound, I'm in the positive y's, I look to be in the negative y's, and there's my negative 5.5, my negative 11 halves. So I still get the same answers as before because it is the same equation. It just looked a little bit different. So I'm going to give you a couple of minutes. I want you to solve these two equations on your own. Okay, so if we were to graph this, the 2x plus 1 looks like there's my 2x plus 1, and then my absolute value of 3 plus root x. Looks like this. Where do they intersect? Or x equals 2. X equals 2. Okay? So if I look at the next one, x equals 8. Or sorry, y equals 8 if I'm doing the intersection method. The absolute value of x squared minus 17 gives me kind of a funky looking graph that kind of comes down like there. Kind of has this W looking shape to it. So it gives me 4 intersection points. What are those intersection points?
Positive and negative 3 and positive and negative 5.
Great. Okay? So that's solving these graphically. Solving them algebraically takes a little bit more work because when we solve them algebraically, we have to go back to what our absolute value expressions were. Our absolute value expressions could be written in piecewise notation. So we have that positive piece and then we have that negative piece. So we have to consider that when we're solving these algebraically. So the first step is to find the values of the variable that makes the expression within the absolute value symbol equal to 0. That's going to give you your subdivisions. Then you're going to divide the domain into the smaller subdivisions using that value you found in the first step. Write the the expressions in piecewise notation. Solve each equation in each domain, and then check that the solution is valid for that domain. I'll show you what it means. We go back to the absolute value of 2x plus 3 equals 8 because we already know what the answer to that is. We already graphed that. So if I was to follow the first step, I let 2x plus 3 be equal to 0, and I solve for x. And I get negative 3 halves. So there's my split in my domain. Now that I have my domain split, I have the part of the graph that's greater than or equal to negative 3 halves and the part of that's less than negative 3 halves. The part that's greater than or equal to negative 3 halves, that's the positive end. That's the positive when this is greater than or equal to 0. So that was this equation right there. So I've got the absolute value of 2x plus 3, which I just removed the bars, the absolute value signs. I get 2x plus 3, subtract by 3, divide by 2. And I get x equals 5 halves. Check, is 5 halves greater than negative 3 halves? Yes. The other side, this is the part where 2x plus 3 is less than 0. So I get less is equal to negative 3 halves, which makes this negative. When is this less than 0? When this value here is a negative. So I put a negative in front of it. So I get negative 2x minus 3 equals 8. Add 3 to each side, and I get 11. And then I divide by negative 2. And I get negative 11 halves. And then I go back and I check. Is negative 11 halves in the subdomain? Is it less than negative 3 halves? Yes. So then my solution would be both values. Negative 11 halves and 5 halves. So now if we look at the next one, Haley solved the equation, the absolute value of 3 plus x equals 2x plus 1 algebraically. So it says, complete Haley's work and compare it to the solution with the one from class example 1a. So if I look at this, if I let 3 plus x equal 0, and I solve for x, x would equal negative 3. So that's what goes in the middle. And then I have the part of the graph that would be greater than or equal to negative 3 and less than negative 3. So this part here, this is the part where it's 3 plus x has to be greater than or equal to 0. And that's where I get x is greater than or equal to negative 3. And this side would be the piece where it's less than 0. So the part that's greater than 0 is just the positive answer, which is just removing the absolute value symbols. I'm going to subtract by 1x, which will leave me with x, and then subtract by 1, and I get that x equals 2. Is 2 greater than negative 3? Yes. So this is in the subdomain. So now if I look at the other one, this is when it's less than 0, which makes this negative. So then I remove the brackets. Oops, minus x. So negative 3 minus x equals 2x plus 1. Move the x over, so I'd add this time, and I get 3x plus 1 equals negative 3. Subtract by 1, and I get negative 4. And then I get x equals negative 4/3. Is negative 4/3 less than negative 3? No. So is the solution in the subdomain? No, it is not. And because it's not in the subdomain, my final answer would have to be that x equals 2. I'm going to show you another way that you can solve them, still kind of using the idea of subdomains with the piecewise. When we ask the question, is the solution in the subdomain, the answer is sometimes yes and sometimes no. An alternative method to solve the two pieces of the absolute value equation without considering the domains, which means you have to check your solutions, you have to verify them. So to do that one, what we do is we take our absolute value and we write it as a piecewise. So as a piecewise, it means that the absolute value of 3 plus x can equal 3 plus x when 3 plus x is greater than or equal to 0. In other words, when x is greater than or equal to negative 3. And it's equal to the negative part when it's less than 0. So then, actually, I'll erase this part here. So then if we were to clean it up, I get 3 plus x, where x is greater than or equal to negative 3, and negative 3 minus x, where x is less than 3. Then what I would do is I would take each of these expressions and put them into my original equation. So I'd have 3 plus x equals 2x plus 1. I go through the steps in solving it. So I subtract by x, subtract by 1, and I get x equals 2. So then I put it back into the original equation. The absolute value of 3 plus 2 equals 2 times 2 plus 1. So I get the absolute value of 5, which equals 5. And on the right-hand side, I get 4 plus 1, which also equals 5. So I check the solution. Then I can take the other equation. So I add x to each side, and I would actually subtract by 1, so I get x equals negative, or 3x equals negative 4. So x equals negative 4/3. And then I would check that one. So I'd have 3 plus negative 4/3 on one side, and 2 times negative 4/3 plus 1 on the other side. So 3 plus negative 4/3 would be 9/3 plus negative 4/3, which would give me 5/3. And this one would give me negative 8/3 plus 3/3, which would give me negative 5/3, which does not work. So then that would eliminate negative 4/3. Okay? So if we look at class example number 5, consider the equation x squared minus 9 equals 7. Solve the equation by graphing, and then we're going to solve the equation algebraically. So if we solve it by graphing, for me, I find the easiest way is to find the intersection. So y1 equals the absolute value of x squared minus 9 is going to give me this equation that looks like this. And then y equals 7 will give me a line that goes through like this. And I need to find these 4 intersection points. So we get positive and negative 4 and positive and negative 1.41. If we solve the method algebraically using what we did in the previous example, I have 2 equations. I have the equation which is just x squared minus 9 equals 7. And then I have the equation which is negative x squared minus 9 equals 7. So if we solve the first equation, the positive equation, add 9 to each side, I get 16. Take the square root of 16, and I get positive and negative 4. So then if I check that, I get the absolute value of 4 squared minus 9 equals 7. Or sorry, it's supposed to equal 7. Which is the absolute value of 16 minus 9, which is 7. If I take the negative, I get negative 4 squared minus 9, which is also 16 minus 9, which also equals 7. So that solution works. That's a good solution. If I look at the other equation, I get negative x squared plus 9 equals 7. So what I'm going to do is I'm going to move my negative x squared to the other side of the equation, which would make it positive, and then I'll move my 7 over, which would make it negative. So I get 9 minus 7, which is 2, and I get x equals the square root, positive and negative square root of 2. So when I go to put this into the equation, I get the square root of 2 squared minus 9, and that's the absolute value of that. So I get 4 minus, or sorry, not 4, 2 minus 9, because the square of the square root of 2 would be 2. So I get negative 7. And the absolute value of negative 7 is 7. And the same thing, if I take the negative root 2 squared minus 9, and I take the absolute value of it, I get negative 2, not negative 2, positive 2, sorry. I get positive 2 minus 9, which is negative 7, the absolute value of which also equals 7. So that makes this a good solution as well. And if you take the square root of 2, what do you get? 1.41. I get that decimal answer. The difference between the 2 methods comes with this right here. In the graphing method, I can only come up with an approximate value. Whereas in the algebraic method, I can come up with the exact value. I can tell you that the solution to this is exactly the square root of 2. It's exactly the negative square root of 2. It's not negative 1.41. Okay? So there are the questions that I would like you to work on.